So we're learning about forces today in chapter 4. The big idea in this in section 4.1 is that net forces cause a change in motion. So if something is moving, accelerating, you have motion. You have a net force causing that motion. So conversely, if something is not moving and staying still, you have no net force acting on the object. Also, if something is staying the same speed and not changing, you also have no net force acting on the object. The only time you have a net force is if it's speeding up or slowing down. So you're driving in a car and you have your eyes closed. If the car is going at constant speed and it's a smooth road and you're not taking any turns, you would not be aware that you're moving because you don't feel a net force on the car if you're going the same speed. Now you do know if you're taking a turn, if you're slowing down or speeding up, because then you're applying a force to cause those things to happen. But without a force, you're not aware of motion. Motion itself does not involve a force. It's a change in motion that involves a force. And that's why right now we're on Earth, we're going very, very fast, but we don't realize it because we're not changing our speed.
So even if we slow down like 1 mile an hour, would we feel a big difference?
Yeah, 1 mile an hour difference is hardly anything. It's not a very big force. So it is a force, but it'd be hard to be aware of that small change. You usually need a larger change to be aware of it.
Like, no, but I'm talking about the rotation.
Yeah, the same thing. And that's a small change, it has to be a pretty big change for you to be aware of it. A lot more than 1 mile per hour difference. Because the Earth is slowing down. It's just taking a very long time for that to happen. We're not aware of it because it's just so slow. Okay, the main idea, so we're going to do several main ideas in this chapter section. The main idea from 4.1 is that a force is a push or a pull. So applying a force either involves pushing an object or pulling an object. Some forces result in motion, others don't. Okay, so you can press against the table, but it doesn't move because you need more force to make the table move than what you're applying to it. So not every force involves a motion. But if you can overcome the frictional force in the table, then you make it move. And so the table will push back on you with an equal opposite force. So if you push forward with a force of 50 newtons, the table pushes back with 50 newtons of force. It doesn't move. But if you push with 100 newtons of force, the table might move because it can't push back with the same amount of force. So if they're not balanced forces, then you have a movement at that point. So you can overcome friction and make things move. If you can apply more force, then friction can give back to you. Now don't worry about those ones. So I mentioned this earlier, but it's worth going over this again, that acceleration is the rate at which the velocity of an object changes. And forces, net forces, cause things to accelerate. So with a net force, you have acceleration. You have a change in motion. You either have a speeding up or slowing down or turning of an object. Those all result in acceleration. Yeah, don't worry about those ones. We'll get to those later. Actually, on this slide really fast, let me go back for a second. Sorry, I didn't make these, so there's a lot that I'm not going to go over. I went back way too far, sorry. So don't worry about that. We already defined the force. Don't worry about those first two. The last one, though, so the last bullet point on here, in your book, what you're going to see is that if it's a bold letter, it means it's a vector. So bold variables in your book mean that they're vector quantities. So those involve direction. So anything that's bold in your book would involve direction with magnitude. So force is a vector quantity too. You always would want to say the direction of force being applied, not just the magnitude of force, like 50 pounds, but you want to say which way is the force being applied to. So when you step on the earth, you're applying a downward force onto the earth. If you weigh 120 pounds, you're applying 120 pounds of force onto the earth's surface. And you're saying it's a downward force. So we always would include not just the magnitude, 120 pounds, but also the direction, which would be downward force in that case. So just the last bullet point in this slide. So as I mentioned, forces can cause things to speed up, slow down, or change direction, which that means accelerate. Any of those things that happen, you have acceleration. And that's evidence that a force is being applied, that a net force is being applied when that happens.
So to my understanding, speeding up and slowing down are the only two, because if you change direction, you're just accelerating in a different direction.
Well, yeah, acceleration would be any change in velocity, right? And velocity is speed and direction. So if you change your speed or you change your direction, your velocity has changed. And that means your acceleration has also changed.
So how do you change the direction without speeding up or slowing down?
Like you're on a highway, like on cruise control, and you're going around a bend on the highway, but you don't change your speed. You're going at 45 miles per hour the whole way. You know, so you're maintaining a constant speed, but you're turning. No, on this slide, skip the middle bullet point, but the bottom one you should know. So all accelerations are the result of an unbalanced force acting on an object. So with balanced forces, you never have acceleration. If it's a balanced force, it stays still or it goes at a constant speed. Unbalanced forces, though, you have an accelerating object. There's the first and the third one on this slide. Okay, so when we're looking at forces and how they act, we define a system. And a system, as you can see in this picture, it's circled. The object that is moving is the system, in the case of the book. So the system is the object that we're applying a force on. So if we're moving a book across the table, the book is a system. It would be good too to draw this picture, draw the forces that we see on here along with the picture. This is a force diagram where we're drawing the directions of the forces acting on the system.
Is this different from a free body diagram?
It's really the same thing. I mean, it's exactly the same thing. So we define the system as the object of interest, and then the external world would be everything else around the system. So everything around the object that exerts a force on the system is called the external world. So that would be the hand on the book. That would be the table. That would be gravity pulling down the book. So we can see in here that the hand exerts a force on the book to the right. Gravity pulls the book downward. Now, what's surprising, so those two make sense, but the one that might surprise you is the third one, the upward force. So the table exerts an upward force on the book, which we don't always think about. But if the book is staying still on the table, you have to have an upward force to counteract the downward force of gravity. And so gravity pulls the book downward, but the book is staying still, you have to have an equal opposite upward force to keep the book in place. And that's what the table does. The table exerts a force against gravity to keep the book on the table. So if the table is flimsy, the book falls through, then the table cannot exert enough force to keep the book up. You have a question, Santi?
Yeah, I was gonna ask if we're gonna learn force notation.
A little bit.
It's like
I mean-
force, kind of force, object being acted upon, and then the object acting.
Wait, say again? I can't hear
It
everything you
was
said.
like, for example, for the force the table exerts on the boat, it would have been like F and
Oh, yes.
BT, because force
Mhm.
neutral on the book by the table.
Yeah, we'll learn part of that. We'll learn a normal force, like the Fn, normal force. We'll talk about that notation. So that's part that we will learn about in this class. So if the book weighs, say 3 pounds. The downward force of 3 pounds starts on the table pushes up also with 3 pounds of force. So the book stays in place.
And so that would be 3 newtons?
No, a Newton is about 1/4 pound.
Okay.
So 3 pounds of force would be about 12 Newtons of force.
So how much is newtons a measure of?
It's also force. Yeah, pounds and newtons are both measures of force. Don't worry about writing this down. You don't need to, just make sure you have the diagram down for right now. Oh, do you need those last notes again? I'll go back for a second. If I can go back. Well, gosh, I'm at the beginning. Let me go back. What was your question, Santiago?
I was just trying to think because the equation for Newton was like mass times velocity over time, right?
For Newton, almost, not exactly. No, actually, sorry, go
I
that
was
way.
just trying to figure out how many newtons the book would have been exerting on the table and that sort of thing.
So Newton's about 1/4 pound. So if the book weighs 3 pounds, then that's about 12 Newtons of force. Just
How
take
does that
number,
correlate to the 9.801? How's that
that's
factor in?
different because that's the acceleration due to gravity. So you could take the mass in kilograms and multiply it by 9.8. That would give you Newtons. So if the book has a mass of say 1 kilogram, multiply it by 9.8, that gives you how many Newtons the book weighs.
So the Newton system is based off of 1 kilogram?
It's based off kilograms, yeah. So you would take the mass in kilograms times 9.8 to get the weight in Newtons.
I was thinking gravity has to be involved because if gravity wasn't there, the book wouldn't be exerting any force on the table.
Mhm.
But so what factor do you multiply mass to achieve newtons?
9.8, yeah.
Yeah, so
Yeah.
kilograms by 9.8.
So you would take, so kilograms times meters over second squared is the units for Newtons.
Kilogram meters per second squared,
Kilograms times meters over second squared, yeah.
1 meters.
Why meters? Well, that's the acceleration unit. Meters
Okay.
per second squared is 9.8 units. On this slide, write down this, the contact force exists when an object from the external world touches a system and exerts a force on it. And so the hand exerts a contact force on the book. In order to make a force on the book, you have to touch your hand to the book. So that's a contact force when you do that.
Does gravity count?
That's a good question. So gravity can go between the air, right? Or between space. So gravity is not a contact force because it can exert a force without touching things.
What about force neutral?
Do you mean the normal force?
Yeah, sorry.
That like a surface exerts upward?
Yeah.
So that would definitely be contact. You only have that when you touch the table or a surface.
Okay.
So there are some that are contact forces, others that are called field forces that can move through space. And so gravity would be called a field force. But others like friction, that's a contact force because you have to actually touch something to get friction.
Well, so you were talking about gravity then, right?
Mhm.
So if that's the case, then is skin drag a contact force?
Because you're contacting either the air or a surface, but you're touching matter to make drag happen, whether it's
So
air.
So are Tachyons not matter?
No, they're particles. Well, I mean, it depends on who you ask about that. But,
Gravitons are purely theoretical, right? But
yeah. But it's possible that, I mean, so they go back and forth about that. Let me just see really fast. I'm happy just wrote something in an email. Let me see what this is about. Oh, wow. Okay. Well, this is the last day of class this week.
What?
Yeah. Hold on, guys. Not leaving just yet. Wow. Okay.
Wait.
So today's the last day of class. So they'll shut down the rest of this week.
Wait, so are you
Um,
homeschooling or?
Well, let me see really fast. So it looks like this week we'll postpone your test or quiz till they return. So we won't have tests over this break.
Let's go. I didn't say at all.
Wow, my goodness. Well, I wonder if we could still have take-home tests like for those who like were studying for a test. I wonder if we could still.
No.
let me ask you this, Holly.
Okay, but as long as,
First off,
listen.
this take-home test.
Wait, Miss Holly, if we study for a test, are they gonna like move it for like 2 weeks?
It sounds like it. I mean, based on what it sounds like that's what she's saying.
That's fair.
That's really hard if you're studying for a test. That's really hard. Okay, so I guess we'll come back next Thursday.
Wait, who's on the Zoom
Hold on, Isabel. I mean, it sounds like that everything's gonna be like just postponed until next Thursday. So it sounds like,
Wait, is there someone on Zoom right now?
no, let me see. Wait, no, you know what? It's not that clear from the email, but it sounds like what she's saying is that we still will have class work assigned, but just no tests or quizzes. So that is, she's not really clear, but that sounds like what she's saying, which means it sounds like you should still bring your books home. Because I think it's not clear, but it sounds like we'll still have class online this week, but you'll still do work at home for this week,
Wait, hold on.
but just no tests. Do what?
There's no fundraisers at all. We're not gonna be
Yeah, yeah.
I'm so glad I didn't put those signs up. Thank you, Ms. Meyer.
Yeah. And so it sounds like you'll still have homework this week when you're at home, just no tests or quizzes.
Oh my gosh, I literally called it.
No, you called me was after
Okay.
break.
No,
Yeah,
I said.
you called me was after break.
Be in school.
So I think at this point, you still plan to have Zoom classes this week for some class. It depends on the teachers and they'll email you. But it sounds like that would be the plan. For the rest of this week, you still will have online classes. Yeah, I'll plan it. From what I can tell for email, it sounds like we still have classes, which means I would still plan on having Zoom classes with you all at the normal time. But we'll have to see. I'll have to check to make sure that that's true. I'll email you all and we know for sure. But that sounds to me like what we would be doing.
But at 1 p.m. every day, we'll be having physics.
Do what?
At 1 p.m. we'll be
I mean,
having-
that's what my plan would be for right now. I mean, but so for now, that's what I plan on doing. But I have to check to make sure that that's really the plan, because her email is not clear about that.
Like, how can you have class if you like were intentionally having a test Friday or Thursday?
Yeah, I guess you just like go to the next lesson or review. It's up to the teacher on what they would do.
Oh,
But they might not have any class. They might just choose to have no class until you come back.
So Miss Holly,
Yes.
so I just had an idea for lab. I know we're not gonna have it for lab. I was just wondering, you know, we're gonna get a little expensive to build a potato stand.
Okay, but don't.
But I happen to have, no.
I'll have to join and then leave.
Keep it down a little bit.
I happen to have some gas or spring powered air soft.
Why do you need air soft?
I was trying to see if I could work them into a finish line. Yeah?
Yeah, that would be, yeah, you should bring it in. We can figure it out.
I mean, can I bring it?
I don't see why not.
Well, because there's a whole lot like air soft.
Oh, it's like a paintball gun, right?
It's an airsoft.
Okay, so it looks like, okay, I see what you're saying, yeah.
Or like, I could like put orange tape on it or something. I just kind of want to show up.
Yeah, I forgot that is, yeah, probably can't have that at school. Like even if it's that, I doubt we can have that at school. Yeah,
For school policy or state?
I think both. Yeah.
Wait, what did you ask?
I don't, yeah, I forgot. Yeah, I don't think that'd be a good idea. I don't think, like, there's even one kid not here, but at public school where he had a knife in his car. It was like to kind of like open up coconuts or something. And like he was expelled for that, for having a weapon on school.
Wait.
Because there's like a large machete coconut. You know, you see those machetes they use for
Oh my
coconuts?
gosh, oh my gosh, who was
That's
that?
not here. It wasn't here.
Oh my gosh, but who was that? Because we literally, there was someone who actually like cut it. I literally remember that. It was
Oh, you
so-
mean here at Faustina?
I don't know, someone brought like. Yeah.
Yeah,
And then they would,
yeah, I forget who that is now. I forget.
but someone did do that.
Yeah, they did. I forget who that is now. I think a few people did that. I think Maddie Lustig brought him one time, didn't she? I thought she did.
I don't know, I thought it was like a
And then,
guy.
and then a guy did too a while back. Yeah, I think a couple of people have. Yeah, yeah. To cut open things, like to cut open like coconuts or avocados or things like that. All right, really quickly before class ends, let's get through a few more things. So forces resolve interactions. So there's always an agent. There's always a cause, which is called the agent. So the hand on the book would be the agent. The hand on the book is what causes the book to move forward. Without an agent in a system, you have no force. So you have to have a cause, you know, like the hand. Then you have to have a system, which is the book acting on the object. Okay, so the email just was sent out that said to bring home all your books. So I guess we'll plan on having work cover this week. Just depends on the teachers and what they want to do exactly. For me, I'll plan on having Zoom meetings, but an exact time, I'll have to let you know, but I would try to have it the same as we have a normal class day, where at the same times as normal. But we'll see what happens with that. I'll give you an exact time later this evening.
Is there any update on sports?
I haven't heard. I would assume it's still the same, that they're until the 5th. Actually, I think she might have mentioned sports. Let me go back. I think she mentioned sports in the email. Oh, no, she didn't. Never mind. So I assume it's still the same plan, that we'll go back on the 5th with everything.
But is that the Thursday after the election?
Yeah, the 5th is Thursday. Well, it should be 2 days after the election. Election's Tuesday.
This week on fall break is extended.
Well, yeah, because it's from now until
Are
Thursday.
we gonna still have a fall break?
Yeah,
I mean, we
yeah.
Don't have any homework or anything to do.
Well,
That would be a
you
week of class.
would have work this week. From what the email says, you would have work this week. Teachers will still assign you work tomorrow through Friday.
So next week
But-
from Monday. to
But you would not
Thursday.
have work Monday through Wednesday next week, because that's fall break. What I showed you in that picture with the arrows, it's called a free body diagram, which shows you the forces acting on the system. So we draw the arrows, which way the forces move on the object. That's not like a real fall break. You get a whole week off. Did you all get that down? No, I'm sorry. I'm gonna go back. I don't know why it does this. Now I went like really far back for some reason. Okay, so did you get these last notes down on here about the free body diagram?
I just need like the last
Okay.
line.
Robert?
So is air resistance a part, like a force in the external world?
Yes, exactly. Yeah, it's friction. The air molecules hitting the object moving is basically friction that slows it down. Oh, so looking at the ball and the rope, it does it so, I don't know why it doesn't stay on that one for some reason. Try it again. Okay, so this is a ball, like a tether ball. You have a rope pulling the ball upward. And so the rope suspends the ball in the air. It's pulling upward, and that's a tension in the rope that keeps the ball in place. The ball pulls the rope downward. Gravity is what causes it to happen. So Earth exerts a force on the ball, that's gravity, pulling the ball downward. The rope pulls upward with the same exact force, keeping the ball suspended above the ground.
What does it mean by Earth's mass?
So the Earth itself, by the gravity is caused by mass. And so the mass of the Earth is what causes gravity to happen. Mass attracts mass, and that's what gravity is.
All right, so if that's a rope, it's force tension, and if it's a rubber band, is it force pull?
We would still call it tension in either case, whether it's a rubber band or a spring.
Because the rubber band is what's exerting the force.
Right. I mean, so either, well, right. So it's a rubber band or rope or spring, but in any case, they're all exerting an upward force. We call that tension, whether it's a rubber band or a chain or a spring.
Because if you leave a rubber band, or if you leave a string, there's, it's just there, and if you pull on it, it doesn't stretch. It merely transmits the force of blood.
Mhm.
Rubber band, however, adds its own resistance to the force.
Oh, yeah, that's true. Also, we call elasticity, but also would talk about that. But so there are other forces in play, but there still would be a tensional force which keeps it in
So it's
place.
just kind of ignored.
Well, it's not ignored. Well, in this class, yes, we do usually ignore the tensile force and the elasticity.
Using the air resistance as well.
Mhm. Don't worry about those.
You guys ready for some trigonometry?
Okay, I think we'll stop here for notes. Let's go ahead and finish the movie. And go and turn this off.